last time we talked about orthogonality and how to compute orthogonal projections, as well as find the orthonormal basis using Gram-Schmidt procedure. And this time we'll discuss how to solve linear interpolation problem or least squares problem, and then we'll discuss how to think about orthogonality in more abstract setting. So, as you know, the inhomogeneous equation ax equals b need not have a solution. Since we have notion of a distance using normal factors, we can instead ask the closest thing to a solution. So if there's no solution, but maybe there's a notion in which the distance calculated using the norm between ax and b is minimized. So how to make it work that ax minus b is the smallest. And this is called the least squares problem, since the taking length involves squares. So equation ax plus b can be solved if and only if b is in the span of a's columns, as we very well know. So the closest point to b in the column space of A is the orthogonal projection. It's a projection of b onto columns of A. Let's call it b hat. So in order to solve the solving of the least square problem is equivalent to, or minimizing the norm of ax minus b, is the same thing as solving the usual linear algebraic problem ax equals b hat. So first we need to compute this, the right-hand side. But it turns out that it's not necessary to compute it, since it's the orthogonal projection to b. So since b hat is the orthogonal projection to b of b to the columns of space of A, then the difference b minus b hat is orthogonal to A's column. And so if you take the A transpose and act on this with b minus b perp, we'll get 0. So if ax equals to b hat, then A transpose times ax minus b is equal to 0. So conversely, let's suppose that x satisfies this equation. A transpose times ax minus b is equal to 0. Then b minus ax is orthogonal to the column space of A, and ax is the column space of A. So the ax is the orthogonal projection of b to the column space of A. It follows both ways. So therefore, these two equations, this one and this one, are equivalent. So this way, we don't have to compute b hat, and we can just look at this equation here. So to summarize the solution of least squares problem, i.e., finding a vector x which minimizes the norm of vector ax minus b, is the same as solving the linear equation. Well, we can rewrite it like this: it's A transpose ax is equal to A transpose x on b. Take an example. So we have a 3x2 matrix. 1, 1, 1, 0, 0, 1, x on x equals vector 1, 2, 3. So then we can replace minimization of this vector by finding a solution of this equation here. So if we take a transposed matrix, multiply it on the left here and multiply it on the left there. We do a quick calculation, and that gives us the following problem. It reduces to a different problem. So the matrix, the 2x2 matrix is invertible, so therefore we can write x as the inverse of the matrix acting on vector 3, 4. And after the short calculation, we get the answer. It's 1/3, 2/5 times vector with components 2 and 5. Okay, I invite you to do the calculation yourself. So pause the video and then find the least square distance for vector x which satisfies this equation. Okay, so let's revise the orthogonal projection, what we know so far. So one way to find the orthogonal projection to V is to determine the orthogonal basis, V1 through Vk of V, and then use these vectors to find the orthogonal projection. So we take, as we discussed in previous videos, the dot product of vector. So if you want to find a projection of B onto space V, you find the projection of vector B on each of the basis vectors Vi, and then take the sum. And individual projection of each vector looks like this, right? We take the dot product of B with Vi and then divide by the length of Vi squared. Here's another way. So we take the basis, any basis V1 through Vk of V, and let A be the matrix with its elements, with its columns. Now, finding the orthogonal projection of B to V is the same as finding a least squares solution for Ax equals to B, right? And then computing Ax. So that's another way to say it. So in other words, this vector B perp or B hat will be equal to, well, it will be a solution of this equation, right? So it will be A times A transpose A inverse times A transpose acting on B, right? And in this case, that the basis was orthonormal. If it's orthonormal, then A transpose some 8 is the identity matrix, right? So therefore the equation simplifies. So we have B hat is equal to B. Now, suppose we're given the data x1, y1, x2, y2, etc., xn, yn, for which we want to the closest fit line, right? It's like the fit in. It's an application, right? So let's see where this. So that's the kind of the setup. Now let's talk about applications. So you have a bunch of points on the plane, and you can ask yourself, what's the closest fit line, right? So say we have we can take the sum of distances from, so that the sum of differences between the values of the function, squares of the values of the function is minimized, right? So that's why it's called least time square. But since we want to fit the line as a linear function, it means that we are minimizing the following, we are solving the following minimization problem. So we need to find the two coefficients, A and B, of the line, right? Such that the following is true, right? So we have a n/2 matrix acting on AB, and that's equal to a vector of coordinates y1 through yn. And we find the, yes, we need to find the value of A and B such that the length of this vector is minimal. Right, so we can apply our method. So, and that's what the computer does, or whenever it needs to fit the data of, say, physics experiment or some statistics data onto a line. Right, so you would measure the differences between the values of the points, of which points to the line, and then you would write the big minimization problem. Okay, so I'm not sure that those of you who work with from the applied math or from economics, you've seen this before. Here's another picture of that. So when the harvest is being collected, right? So these trucks, they follow this line. Let's talk about abstract properties of the dot product. So the first one is distributivity or bilinearity, right? So basically, if you have It's a fancy name for a rule of how to open up parentheses. You have, well, AB plus BB prime dot with CW plus DW prime, and it's equal to the following four terms, right? So just whenever you have the vectors, you put the dot product. It is commutative, right? So VW is equal to WV, and it's positive. So the a vector dot product with itself is always non-negative, and it's only equals to 0 when vector V is equal to 0. Now, that was the dot product in real dimension, in the real over real vector space. Now, let's talk about a bit more abstract inner product. So it's a generalization of the scalar product. So an inner product of a vector space V is this bilinear map, which we denote with brackets with two positions. So of V cross V into R, which is distributive, commutative, and positive. So these are the rules, right? But there will be slight modifications. You want to work over complex numbers. So let's look at an example. Right, so we call it a polynomial of degree n. It's determined by evaluation of at any n plus 1 distinct real numbers. Right, so you can find all the coefficients. So let's pick numbers R0 through Rn, which determine an isomorphism from a space of polynomials of degree up to n to Rn plus 1. And so it's the evaluation map, which takes a polynomial and evaluates it at this point. And this determines a function of pairs of polynomials, right? If you have two polynomials, f and g, you can calculate inner product with them just by declaring that it's the product of the evaluations of those polynomials at this tuple of points. So it is an inner product because we can explicitly check its properties, since they also hold for the dot product. Another very common example is a space of continuous functions on an interval. And the pairing is defined as an integral of the product of these functions over AB. So because they're continuous on a closed interval, integral always exists, right? This function is integrable, and we can define the inner product like that. So it's clearly distributive and commutative, and it's positive because if f is a non-zero continuous function, then integral is non-negative. So it's an integral of a square of a non-zero function. The integral inner product is a continuum limit of evaluation inner products. Now, say you want to take a series, right? So the if you want to take a space of polynomials with degree up to n, and then you send n to infinity. So there is this formula that you will take a sum to take f, the two polynomials f and g, right? And then you would send n to yes, like this case, evaluate it at points which are equally spaced by interval 1 over n, multiply them together. So you take a partition of interval AB, then you would evaluate it at every point of the partition, the product of functions f and g, right? And then you divide by n, which is the mesh of the partition, and then take the limit. You can check that indeed gives you, more or less by definition, the Riemann integral from A to B. Let's talk about length, distance, and orthogonality in more abstract sense. So an inner product of a vector space determines the notion of length, right? So we can take a vector, take an inner product with itself, and then take the square root. That's the norm or the length. If you have two vectors, so a vector is in one-to-one correspondence with a point, right, in some n-dimensional space. So therefore, the distance from A to B is the norm of the difference of these vectors. and orthogonality. So vectors are orthogonal if the inner product between these vectors is equal to 0. As an example, consider the vector space SIC of all infinite sequences of real numbers, E1, E2, E3, and so on, for all possible values. So it's a huge space. Now, it's tempting to define in a product like this, right? So you would multiply each term, you multiply them term by term, and then take the sum. You'll get a series like that. But the sum need not converge, right? I mean, it's of course there are a bunch of sequences that converge, so that but when you multiply them together, you'll get a divergent series. There are plenty of examples like that. So even like if you try to do the length, that will not be that may not be defined, right? So if you take the vector dot include itself and then take a square root, then this also may be divergent. So we need to come up with a better idea. So we need to consider sequences such that the sum is actually finite. So it will be a subspace of those sequences, subset, right? And this is called L2. For example, 1, 1/2, 1/3, etc. is an L2, right? So if you take squares, you have sum of 1 over n squared, which is convergent. And moreover, we know that the answer is equal to pi squared over 6. But if you take this one, then it's not going to be convergent because the harmonic series sum 1 over n diverges. So one can check that L2 or L squared is a subspace. So given two sequences in L2, we can have both for each finite n, right? So let's calculate the partial sum, right? So partial sum of this distance formula, right? So the square root of sum from 1 to n of ai plus bi squared, which is the norm of ai plus bi. And then by the triangular inequality that we discussed previously, this is less or equal than sum of norms of these individual vectors, or it's equal to this formula, right? And then because they all, and then you can take the limit, right? So and we know that both sequences, they belong to class to this set L2, and therefore, if the right-hand side is convergent, therefore the left-hand side is convergent, which means that the sum of the vectors also belongs to L2, so which shows that the subspace is closed under the addition of elements. And now the formula here is finite on L2, right? So because you can write it like this, you can take the for every sum, you can take the product of ai and bi, and this just from algebraic manipulations is equal to 1/2 sum of ai plus bi squared minus sum of ai squared minus sum of bi squared. And we just showed that each of these terms belong to L2, and therefore if you take linear combination of them, they also belong to N2. So there's the distributivity, commutativity, and repetitivity properties. They hold the same reasons as for the dot product before. Thus, we have defined an inner product on space of L2. Now, I consider another set, which we call fin-seq, of all sequences whose entries are eventually all 0. Right, so then it will be a subset of L2, since obviously the sum of the squares is actually finite because it only has finitely many non-zero elements. Right, so it has a basis, so it's a finite dimensional space, vector space, and the analog of the canonical basis here will be formed by vectors ei, where the sequence, which is a sequence of all zeros, except there's one at ith position. Now, for any vector A from L2, we have inner product of A with AI, which is equal to the coefficient AI. And it's the expansion, it's the coefficient, well, it's the coordinate of this vector in basis of those AIs. So the orthogonal complement of the set phin6 is equal is the zero vector subspace, which consists of zero sequence. Now you can see here that unlike in the finite dimensional case, right? So this sequence 1, 1/2, 1/3 cannot be written as the sum of something in phin6 and something in the orthogonal complement to phin6. Right, so remember in finite dimensional vector space case we had if you take the orthogonal complement to orthogonal complement, we return back the same subspace, but here this is not the case, right? So if you take so phin6, so orthogonal complement to phin6 is the zero sequence, and orthogonal complement to that is the entire vector space, the ambient vector space of those sequences with finite series convergent, with finite sum of AI squared. And that clearly does not contain in phin6, right? So it's not the, so I mean, it's much bigger than phin6. So therefore, this is not true. So this property about orthogonal complement of the orthogonal complement, they do not apply for infinite dimensional spaces. Moreover, orthogonal projection to phin6 is not well defined. Now let's talk about Gram-Schmidt. So in a finite dimensional vector space with an inner product, we can take a subspace W and write W perp for the set of vectors whose inner product with anything in W is 0. Now, any vector V can be uniquely decomposed as W plus W perp, where W lives in the subspace and W perp lives in the orthogonal complement. And this holds by the same proof as above. Right? So it works for the, I mean, the same proof as we did for the dot product can be directly generalized to the inner product. So make sure you follow the proof from the previous lectures and then challenge yourself at which point we use finite dimensionality. So, and we can construct a counterexample when this space is not finite dimensional, it's infinite dimensional, where the statement is not true. So any vector can be uniquely decomposed from the subspace and its orthogonal complement. Okay. So what's the orthogonal projection? We take orthogonal bases, W1, Wk for W. So they are inner product with two different vectors is equal to 0 if vectors are different. So we can write a similar formula for the orthogonal projection. We just replace the dot product from the beginning of the lecture by this inner product. And then orthonormal basis can be found by applying Gram-Schmidt process to this case. Now, let V be a finite dimensional vector space with an inner product, and let B be a basis. So because it's a basis, any vector can be uniquely expanded as a linear combination of the basis vectors. And we can write V subscript B for this vector. Now, this gives us V to VB gives us an isomorphism from V to Rn, where we should be able to express the inner product just in terms of this basis vector, this basis. now we take the matrix of inner products of the basis vectors between themselves. So that's the ij's entry is equal to this number. And we can write, take the inner product of two vectors, v and w, and then we do the basis expansion of the basis vectors of each of them, and then we apply linearity properties. So we'll get it like this. We get sum over I and j, bi, times this matrix with entries bi, whose ij entry is bi, bj, and multiplies by wj. So if you write it as a matrix, it would look like you take a row vector v, so it's v transpose in this basis, then you multiply by the matrix, and then you multiply by column w. And that will give you the number, right? Because 1 by n column multiplied by n matrix, row, excuse me, multiplied by n matrix, multiplied by the n by 1 column is a number, 1 by 1 matrix. Now, if the basis was orthonormal, then the basis is the identity matrix, right? And then we just take the inner product is simply the product of a row vector and a column. And then, well, as you know, the orthonormal basis always exists because we can apply Gram-Schmidt procedure. And the inner product looks like the dot product in appropriate basis. Now we can classify inner products. What are all possible inner products on n-dimensional Euclidean space? So we can take the standard basis, right? And then in the inner product determined by the Gram-Schmidt matrix, it's called, sorry, Gram matrix. So that matrix we'll call it Gram matrix, which is the this matrix of the bilinear form of the inner product. So this matrix over here is the matrix in a given basis, which defines the inner product of two vectors. Now, this matrix is always symmetric, so which means that it's equal to its transpose. So if we replace I by j, it should be, so Eij is ij's component is equal to the ji's component. And that follows from commutativity of the inner product. And then conversely, for any symmetric matrix M, the map Rn cross Rn to R, which takes two vectors and maps them to the V transpose MW, is automatically distributive and commutative. So in order to classify inner products in terms of matrices, it remains to understand when this map is positive. So that's what's required for the inner product. So let's look at an example. This matrix is positive, right? So if you take AB row multiplied by this matrix, multiplied by AB column, it shows you that's equal to A minus B squared plus A squared plus B squared. So it's a sum of squares, right? And it's only 0 when A is equal to B is equal to 0. So this is positive. Now, if you take 1 to 1 instead, then it's not positive, right? So you can take this vector here, and, which is not equal to 0, 1 minus 1, and then evaluate the Gram bilinear form. So you calculate the Gram matrix, the row multiplied by Gram matrix multiplied by the column, it's equal to 0, albeit, but the vector is not equal to 0. So it is not positive. So more generally, if you have a 2 by 2 matrix with components, it needs to be symmetric, right? So it only has 3 independent components, x, y, and z, right? So then AB times x, y, y, z, and b is equal to this quadratic polynomial, which you can write as b squared multiplied by x a over b squared minus 2 over b y plus z. And the quantity will always be positive so long as x is positive, right? Because it multiplies the square. And the thing in the parentheses over here has no real roots in variable A over B, right? That's a type here. So in other words, so it has to be, because if it has, right, then it will definitely go to the negative values. Right, so, so think of it like this, right? So if you have a parabola, so we'll draw it as a variable A over B, and then let's say parabola like this, right? So if it has no real roots, so because we know that, so if x here is the coefficient here, so if it's positive, then the parabola will be pointed upwards, right? And then if it doesn't have any real roots, then it's always positive. As opposed, if it had real roots, it would do something like this, right? And then there'll be well, some margin here when the map is not positive. Okay. And that can be done just by studying the discriminant of the quadratic polynomial, which is 4y squared minus 4xz, and that should be less than 0, right? So that the quadratic polynomial will not have any real roots. And you can see that this is equal to the -4 times the determinant of the matrix xz yy. So this is equal to, yes, in other words, it's positive when x is bigger than 0 and the determinant of this matrix is bigger than 0. So it also follows from here that z bigger than 0, and since y squared is equal, since y squared is also bigger than 0. Now, the eigenvalues of the above matrix are the roots of this polynomial. That's the characteristic polynomial of this matrix. So twice the, so if t is the variable for the characteristic polynomial, so twice t is equal to x plus z plus minus the square root of x minus z squared plus y squared, right? Sorry. Right, and from the second expression, we see that both are real numbers. So from the first one, since x, so this is real, right? And then this is also real because xz minus y squared is bigger than 0, so everything is positive. The discriminant is positive. Okay.